Hello again. In this video, we're going to go over some of the basic rules that we have for indefinite integrals, which are also known as antiderivatives. Now remember, our notation for an antiderivative looks like this. We use this script S symbol, and then it's followed by the function that we're trying to find the antiderivative of, and then that's followed by this symbol dx, which stands for the differential change in x. Now this tells us what the independent variable is. So in this case, the independent variable is x, which is also known as the variable of integration. And then f of x is sometimes called the integrand. Okay, so the first rule we're going to look at is the power rule. So let's say you want to find the antiderivative of x raised to the p power, where p is any real number except for -1. Okay, so then the antiderivative of x to the p power is x to the p plus 1 power divided by p plus 1 plus some arbitrary constant c. Now, again, this is good for all real numbers p except when p is -1. The reason we can't use -1 for p is because notice that if you plug -1 in for p down here, you'll be dividing by 0. We actually have a different rule when we're trying to find the antiderivative of x to the -1 power. X to the -1 power is the same as 1 over x. And the antiderivative of 1 over x is actually the natural log of the absolute value of x plus an arbitrary constant. And we'll talk about that rule later on. Okay, so that's the power rule. We also have the constant multiple rule. And that basically says if you want to find the antiderivative of a constant times a function, you can find the antiderivative of the function first and then multiply it by the constant. In other words, this constant c can be pulled outside the antiderivative operator or the indefinite integral. Okay, so we also have a sum rule that tells us the antiderivative of f plus g, the same as the antiderivative of f plus the antiderivative of g. And by the way, this is also true if this were a minus sign. So if you say the antiderivative of f of x minus g of x, it's the antiderivative of f of x minus the antiderivative of g of x. Okay, so let's go over an example where we can use some of these rules. So let's say you wanted to find antiderivatives of this function here, or the indefinite integral of this function. Okay, well the first thing we're going to do is we're going to break this up into 3 different indefinite integrals using the sum rule. So this is the same as the antiderivative of this function plus the antiderivative of this function minus the antiderivative of this function. Okay, and then using the constant multiple rule, we can move these constants outside the antiderivative operator. Okay, now let's just go through and find the antiderivative of these 3 different functions. Okay, so here we have x to the 5th power. And so the power rule tells us that anytime we have x to a power, right, x to the p power, the antiderivative of that is x to the p plus 1 power divided by p plus 1 plus some arbitrary constant. Again, as long as p is not equal to -1. Okay, so in this case, p is 5, right? So we can add 1 to the exponent, and that gives us x to the 6th power, and then we divide by the 6. And so that's the antiderivative of x to the 5th power. Now, if you want to check this, if this really is the antiderivative of x to the 5th, then when I take the derivative of it, I should get x to the 5th back. So if you just want to check that, you can. You can pull the 1/6 out of the derivative operator, And of course, the derivative of x to the 6th power is just 6x to the 5th power, using the power rule. And then when you multiply by the 1/6, you get x to the 5th. Okay, so that makes sense. And then there's this 3 in front, so we're going to multiply by that, plus some arbitrary constant, which I'm going to call c sub 1. Okay, now the next one here, sometimes this will happen where there doesn't appear to be a function in here. So the question is, what are we trying to find the antiderivative of, right? What's the function here? Well, we pulled the 2 out. There technically is an imaginary 1 that's left in here, right? 2 times 1 is 2. So if you pull a 2 out, you're left with a 1 here. Okay, so we need to find the antiderivative of 1. Where x is the independent variable. Okay, and that's actually important in this case. So what I'm going to do here is I'm going to rewrite 1 as x to the 0 power. Now, remember, x to the 0 power is equal to 1, right? Any number raised to the 0 power is equal to 1. The reason I'm using x is because we know that the independent variable is x because this is a dx. And of course, the reason I'm raising it to the 0 power is because it has to equal 1. Now, the reason I'm doing this is because now I can use the power rule, right? The power rule is valid for any p that's a real number except -1, so it's good for 0. Okay, so I'm going to add 1 to the exponent, which is going to give me x to the 1st, and then I'm going to divide by 1. And then, of course, this 2 gets multiplied by that, plus an arbitrary constant, which I'm going to call c sub 2. If you want to check this, the derivative of x to the 1st power is 1, right? So it'll go back to this. Okay, now this last one, when you look at this square root, at first you may not know what to do because we haven't talked about the antiderivative of square root of x. But remember, the square root of x can be written as x to the 1/2 power. And that allows me to use the power rule. Okay, so I'm going to add 1 to the exponent. And of course you need a common denominator here, so I'm going to write it as 2 over 2. And that gives us 3/2. So we get x to the 3/2 power, and then we divide by 3/2. Right, using the power rule. Okay, and then that gets multiplied by -5 plus some arbitrary constant, which I'm going to call c sub 3. Okay, and so let's just clean this up now. So this is 1/2. This is 2x. And then it looks like here you would flip this and multiply, so that would be 2/3 times 5, and that gives us 10/3. And then x to the 3/2 power. Then we have c1 plus c2 plus c3, which are just 3 arbitrary constants. Well, those are just 3 different numbers, right? They're constants. So they just add up to another constant, which I'm going to call c. So c is the same as c1 plus c2 plus c3. Okay, so I think that's as clean as we can get this, right? That's simplified as far as we can go. And so this is the antiderivative of this function here. Now, if you want to double check it, just take the derivative of this. And make sure that it's equal to this, right? So if this really is the antiderivative of this function, then when you take the derivative of it, it should go back to this. So that's a way of checking it. So let's just check it real quick. So here the 6 comes down, you subtract 1, multiply it by 1/2. Here the 1 comes down and multiplies by the 2, and you subtract 1, so you get x to the 0. And then here the 3/2 comes down and gets multiplied by the 10/3. and you subtract 1 from this exponent, and that leaves you with 1/2. And of course, the derivative of a constant would be 0. Okay, and so if you just clean this up, this gives you 3x to the 5th, 2x, or actually 2 times 1, so that's 2. And then the 3's cancel here, and then 10 over 2 is 5. And that's just square root of x. Okay, so it does check out, right? It goes back to this small f of x. Okay, so this is capital F of x. Remember, the derivative of capital F of x should be small f of x, right? And in this case, it is. So that's a way of checking to see that you have the correct antiderivative of this function, or antiderivatives, right? Because there's a whole family of them because of this arbitrary constant. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.